Hi. Oh, I'm seeing Mum tomorrow. I thought you were calling about the startup idea. I get that I would be the finance and you would be the physics. Yeah, but what does the physics involve? Go on Zoom, I'll draw you a storyboard. A lot of protective gear is required because the quantum environment is so fragile. We take a piece of silicon and put it inside a holder which we can insert into a clean environment where we put phosphine gas. The particles land on the silicon crystal and incorporate themselves, except that they have an extra electron. The quantum bit is encoded into the state of this extra electron. Now, the question is, how do we control the information in that qubit? Well, we control it electrically. There are our two qubits, and the electrical contacts are actually made of phosphorus. Then we overgrow with a little bit more silicon, and then we need to contact it with a computer so that we can read out and send in information. That's for controlling one qubit, but what about two? Well, that is our innovation. The entangling gate you can do with light. Now you're probably wondering, on my classical computer, how do I code the quantum computer? Well, go to the browser. And IBM have made a free circuit composer. Timelines represents what happens to the different qubits. You can drag and drop single qubit gates. This Hadamard gate creates a superposition on the first qubit. I'll tell you about this later. And you can create an entangled state by having an entangling gate on both qubits. And then, for example, you can measure. We have our Qiskit circuit composer where we can drag and drop gates onto the qubits, represented by lines here. The single qubit gates are electrical pulses, and the 2 qubit gate is the light.
Quantum bits and quantum gates.
Oh yeah, bits. They encode the information, right? 0 and 1.
Yeah.
Binary.
Basically, in a classical computer, you have 0, for example, like this, or 1, like this. But in a quantum computer, you can be in any state in between, like this, or maybe like this.
Whoa, wicked.
Yeah, sounds cool, but there is a catch. A classical state is always classical, whether you measure it or not. But a quantum state, it's really fragile. It loses its coherence as soon as you measure it, and it collapses to the nearest classical state. So actually you need to prepare it and measure it loads of times before you can get a good probability distribution of where it actually is lying.
What about entanglement?
So imagine you and me are both quantum particles. So some experiment prepares us both into an entangled state of 2 entangled particles. Then if I am measured completely separately to you, then I collapse and I collapse to, for example, 1. The experimentalists will know without looking at you that you will also have collapsed at the very same time and that you will have also collapsed to 1 because you're prepared in the same state as me. If you were prepared in an opposite state to me, then you would have collapsed to 0. And if you look from a different direction, so you're measuring in a different basis, the entanglement remains. It doesn't matter in what basis you measure, the quantum correlations will always be perfect.
Do quantum computers already exist? Yeah, with tens of qubits? And if you could have long coherence times, high fidelity entangling gates, and many qubits, you could definitely solve relevant problems. What kind of problems? Well, new materials. And new materials being photovoltaics, efficient fertilizers, new materials for carbon capture. Risk related to financial portfolios, optimization of risk, and transport and logistics, or even new drugs. You could basically use the quantum world to understand our universe at the atomic and subatomic levels. Look, there's money in this. Does that work for you?